In previous lessons, I have discussed what a mathematical function is, limit of a function as the variable approaches some value, and I talked about its rate of change and the derivative, which is defined as instantaneous rate of change of that function. Rate of change of a function with respect to its variable and the limit of this as delta approaches 0, that is the instantaneous rate of change, also called the derivative of the function, are the very core concept of calculus. In this lesson, I will show the graphical representation of rate of change. Let me take an example of a very simple function which I discussed in the previous lesson as well, y is equal to 3x plus 5. This function plots as a straight line. The plot of this function is a straight line. Let us look at the rate of change of this function on its graph. To arrive at rate of change, I take 2 points, any 2 points. I take x is equal to 0. So from this graph I can read out for x is equal to 0, y is equal to 5. The other point I will take is x is equal to 1. For x is equal to 1, y works out to 8. This here is delta x and this here is delta y. From here till here. Rate of change is delta y upon delta x is equal to 3 upon 1, that is 3. Notice in this case, I could have taken any two different points. I take x is equal to minus 2, so y works out to minus 1, that is this point, and x is equal to 1.5, so y works out to 9.5. So in that case, this becomes my delta y and this becomes my delta x. 1.5 minus 2, that is 3.5. Delta x is equal to 3.5 and delta y minus 1 till 9.5, which is 10.5. So for these 2 points, delta y upon delta x, 10.5 divided by 3.5, which is again 3. For a graph, this value delta y upon delta x is called slope of the graph. If it is a straight line there, it is slope of the straight line. Notice this also happens to be tan of this angle. For a straight line, this is tan of the angle that the line makes with x-axis. So tan of the angle that the line makes with x-axis in the terminology of coordinate geometry is called the slope of line, which is nothing but it is the same thing as rate of change. A straight line has a property. Rate of change is same everywhere and rate of change actually does not depend on how big a delta x I select. In this case I selected delta x is equal to 1. In this case I selected delta x is equal to 3.5. In both these cases the slope delta y upon delta x worked out to 3. This is not true for all other type of functions whose plot does not look like a straight line, whose plot does not work out to be a straight line. This condition of the slope being the same, the rate of change being the same all across the length of the function is not applicable for any other function whose plot is not a straight line. In this case, the limit for delta approaching 0, if I take a very small section of this and take delta y upon delta x and try to find the limit of delta x approaching 0, will be the same as the average rate of change for a larger sections. Delta x is equal to a larger value of 1 or a still larger value of 3.5. Because it is a straight line, the rate of change remains constant, and the limit of rate of change for delta x approaching 0 remains the same as the average rate of change. Only for a linear function, that is only for a function whose plot works out to be a straight line. Let me take another example. Area of a circle. A is equal to pi r square. Area here is defined only for positive values of r, and the value of area is also always positive. So the plot of this function will not go into the negative direction of x or the negative direction of y. So here is a plot of area is equal to pi r square. Area is defined only for positive values of r, and area itself is always a positive quantity. So in this case, the graph does not go towards the negative direction of r or the negative direction of area. For r is equal to 0, area is of course 0. For r is equal to 1, I have taken the scale as 1 centimeter is equal to 4 pi. For radius is equal to 1, area is pi. For radius is equal to 2, area becomes 4 pi. 3, area becomes 9 pi. 4, 16 pi. 5, 25 pi, and so on up till I have taken 7. So that works out to 49 pi. I will try to take the rate of change using different sets of points on this. Let me first take 2 points. R is equal to 3, and the second point R is equal to 6. We can either calculate or read it out of the graph. For r is equal to 3, area is equal to 9 pi. For r is equal to 6, area is equal to 36 pi. And the slope, the rate of change, this rate of change 36 pi upon 3. 36 pi here is this delta y, and 3 here is this delta x. So this happens to be the slope of the line joining these 2 points. First point was radius is equal to 3 and area is equal to 9 pi. Second point was radius is equal to 6 and area is equal to 36 pi. The straight line joining them, which the straight line does not coincide with the curve. The straight line joining them, the slope of that straight line is the rate of change. That is why we call it the average rate of change between this point, and it is the rate of change of a straight line. It's the average over this gap. If I reduced delta x from first point at 3, second point, instead of 6 I bring it back to 5. So at 5 the area becomes 25 pi. So this happens to be my second point. This happens to be my modified second point. So now I am talking of average rate of change from this point to this point, which in this case delta y is 25 pi minus 9 pi, which is 25 minus 9, 16 pi, divided by 5 minus 3, that is 2, works out to 8 pi. So the rate of change for this and this pair of points is 8 pi. The rate of change for this pair of points, which covered a wider gap of delta x, worked out to 12 pi. If I reduce now this second time, this pair of points, the rate of change was actually the slope of this little line here in between, not very clearly visible also. The line, straight line joining this point and this point. In the previous case, it was a slope of the straight line joining this point and this point. So as I bring my points closer, the straight line changes. It is called a chord of a curve. It does not coincide with the curve. It goes straight from one point to another point, and this time my average rate of change is the slope of this line. I can bring this scale closer. First point at 3, x is equal to 3, y is equal to 9 pi as before. First point remains the same in my all three examples, and second point I bring it to 4, and area becomes 4 square, 16 pi. 16 pi minus 9 pi divided by 4 minus 3 works out to 7 pi. This is the rate of change, average rate of change when the interval is taken from x, radius is equal to 3 to radius is equal to 4, and this time it is a straight line joining this point and this point, and because of the resolution of the plot, because of the resolution of the graph, this straight line joining these 2 points actually looks to be, it is not exactly, it is actually not so, but it looks to be coinciding with the plot. All that I am doing is, if I have a curve like this, I am exaggerating the curve. First I took 2 points here and here, I joined them, I took the slope of this line, then I took 2 points here and here, I joined them, I took the slope of this line, then I took 2 points still closer, I joined them, but still I am never overlapping the point. I am never overlapping with the curve. If I take the limit, the slope, as you notice, started with 12 pi, gone down to 8 pi, reduced to 7 pi. If I take the limit, which I did in my previous lesson, limit, as we know, works out to limit of what? Limit of rate of change of area when delta x, delta r in this case, tends to 0. This works out to equal to 2 pi r, and for r is equal to 3, the rate of change, limit of rate of change as delta r approaches 0 will be 3 to the 6 is equal to 6 pi. So when I bring this point closer and closer and closer, the limit, which means the 2 points are never allowed to overlap. If they actually overlap, you can't draw a line through them, you can't find the rate of change, delta x is 0, delta y is 0. But in the limiting case, the lining joining the 2 points, their slope will be 6 pi. This is what is called the tangent to the curve, and here I have drawn this tangent. And if you see, take any 2 points on this, on the graph it is not possible to do it accurately because there is a limitation to how accurately you can read, but given mathematics has got no such limitation, I know the slope of this tangent happens to be the instantaneous rate of change of the curve at this point, which will work out to 6 pi if the point here is r is equal to 3. Since I did the calculation and I got a result of 2 pi r, I can change the value of r. If value of r, I take this point instead, r is equal to 1, and I want to find the instantaneous rate of change at this point. If I were to draw a tangent, the rate of change at this point will be 2 pi r, r is equal to 1, so it will work out to 2 pi, which the slope of this line will be only slope of the curve at this point, which is the slope of the tangent at this point will be only 2 pi. The slope of the tangent at this point works out to 6 pi. As is very obvious looking at the curve, the tangent here is less slopy. The tangent here is more slopy, and as we go up the line, the tangent becomes more and more slopy. So the instantaneous rate of change of a function is same as the slope of the tangent to the curve obtained by plotting that function at that given point. To repeat, derivative of a given function, which is the limit of rate of change of the function, limit as delta x approaches 0, is slope of the tangent at the given point, and it is limit of delta y upon delta x as delta x approaches 0. Now given that, supposing I know for a given function I know f dash x at this point, and I know the value of the function at this point. That means I know the value of y at this point, this specific point, and I know f dash x, and I want to find out an approximate value of the function for another point, which is delta x ahead of the first point. At x plus delta x, I want to find out what is y plus delta y, or in other words, I want to find out delta y given delta x. So now that we know that limit of for delta x approaching 0, for a small but finite non-zero value of delta x, this would become an approximation, and the approximation will become more and more correct as the value of delta x reduces more and more. Notice this delta is used to denote for quantities which are very, very small, infinitesimally small, approaching 0. This delta is used for change in quantity, change in value of a quantity, not necessarily infinitesimal. So if this distance delta x is not infinitesimally small, then the slope of this line will only approximately equal the slope of the curve at this point, because then we are talking of the average slope from this point to this point, and f dash x is the instantaneous slope. Instantaneous slope will equal average slope if the value of delta x is small. So using this approximation, I can say delta y is approximately equal to delta x into f dash x. Let me take an example of area is equal to pi r square. For r is equal to 2, we know area is equal to 4 pi, and we know a dash, which is derivative of a, derivative of pi r square, is 2 pi r. For r is equal to 2, a dash is equal to 4 pi. So what is going to be the value of area when r is slightly more than 2? Let me say 2.1 centimeter. Delta r is equal to 0.1 centimeter. Delta a will equal delta r into a dash, delta x into f dash x. Delta r is 0.1, a dash is 4 pi. So delta a will approximately equal 0.4 pi. So area for r is equal to 2.1 centimeter will approximately be the area at 2 centimeter, which was 4 pi, plus this approximate delta A, 4.4 pi.